Hey everyone, welcome back to Calculus 3. This will be lecture 12 of the course, and this will probably be on the shorter side. What we're going to do here is we're just going to introduce functions of several variables. So if you're taking Calculus 3 for the first time, and you've not taken physics yet, you maybe haven't run into functions of several variables. So you've seen a function of single variable only. And so some of the notation, some of the way of thinking about it might need to be addressed. And so that's kind of the purpose of this section. Okay, so let's jump into it. So this will be section 3.1, Intro to Functions of Several Variables. Okay, and so far we've really only dealt with functions of one single independent variable. So things like f of x equals 2x squared, for example. You have just a single independent variable x, and that's it. And that's kind of what we're used to seeing. That's what we're used to running into, specifically in calculus classes. But many quantities can be thought of as functions of two or more variables. Okay, so many quantities are functions of two or more variables. Right? So, simple things like the volume of a right circular cylinder, for example. Right? Like a right circular cylinder, if you think about what that looks like, here you got the top, and then you've got, some height here. And if you think about the volume of this, right, the volume here is equal to pi times the radius squared times the height, basically the area of the circular base times the height, right? And so this is really a function of two independent variables, r and h, right? So this is a function of r and h, and therefore of two independent variables. Okay, so this is a simple example, right? One that we've seen. Also, another one would be like the volume of a rectangular solid, right? If you take some kind of a rectangular solid, maybe something that looks like this. Okay, the volume there is equal to the length times the width times the height. All right, so this is a function of three independent variables. Okay, so this is a function of three independent variables. Right, now what we're going to be moving towards is going to be more general. These are examples from geometry that we are somewhat familiar with, but what we're going to move towards are going to be more general things. And so let's talk about what the notation looks like for functions of several variables. Right, so if you have something like this, f of x y equals x squared plus x times y. This would be an example of a function of both x and y, so two variables. Okay, so a function of x and y. And this is generally speaking how these things are going to be notated. So instead of just an f of x, you would say f of xy. All right, similarly, if you have three variables, this would be something like x squared plus x squared y z or something. So this is a function of three variables. All right, so you can kind of get the picture here. All right, so you can just list whatever variables are in the function just inside the parentheses in this manner. That's kind of how this stuff's notated. Okay. Now the whole thing can be, extended indefinitely, right? I mean, in Calc 3, we're going to be mostly concerned with 2- and 3-dimensional functions that are that have 2 or 3 independent variables. But technically speaking, you could have something that is a function of n variables, right? And so that would be denoted something like this, right? So an arbitrary number of variables is totally possible. Okay, so in this case, n variables. Okay, all right, so that's kind of how these things are notated, how we tend to think about them. What happens with the domain of functions of several variables? Well, I mean, you have the same considerations as before, right? You can't divide by 0. You can't, if it's a real valued function, you can't take the square root of, a negative number. Those are the main concerns from the previous, from functions of a single variable, and those persist here as well. But in addition to that, you have to sort of consider the variables in conjunction with one another, right? So let's do an example. Let's find the domain of this function. So this would be x squared plus y squared minus 9, and the square root of that all divided by x. Okay, so what's the domain of this function? Well, we know straight away that x can't be equal to 0. So 0 is not in the domain of this function. So that's sort of the can't divide by 0 concern that we're all familiar with, right? So we know that x can't be 0. What else is of concern here? Well, the square root, we want this to be a non-negative, right? Otherwise you're introducing imaginary numbers into a real valued function, right? So we also need x squared plus y squared minus 9 to be greater than or equal to 0. Okay, and so what that basically means is that x squared plus y squared needs to be greater than or equal to 9, right? And so if you look at this, in this particular example, if you look at this, you can see that this is indicating a circle, right? So this is indicating a circular region. Okay, and so I'm just going to draw this here. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and this is going to be a circle with radius 3. Right, so x squared plus y squared needs to be greater than or equal to 9. So x squared plus y squared equals 9 is a circle with radius 3. Right, and so this is a circle with radius 3, and so what this is saying is that in order for this function to be real valued, first of all, x can't equal 0, and second of all, x plus y together, when you square them and add them together, they have to be greater than 9. Right, and so that basically means the domain is this whole region outside of this circle. Okay. So it's this region outside of the circle. Okay, and so that together with the fact that x can't be equal to 0 means that, well, so technically the domain would extend up the y-axis and down the y-axis, right? X has to be off the y-axis and it has to be outside of this circle, right? So the domain is, you could say it like this, it's x and y in R such that x is non-zero and x squared plus y squared is greater than or equal to 9. That would be kind of the best way to say it, right? So you can kind of see that in the case of functions of several variables, you have to take into account the two variables separately. So it isn't as easy always to demarcate the domain in the case of these functions. Let's do one more example like this. Let's do another example kind of similar to this. What about this one? Find the domain of and we'll write, this will be f of x, y, and z, and that needs to be equal to x divided by 9 minus x squared minus y squared minus z squared, square root of that. Right? So it looks quite a bit different. Okay, so here again, well, x isn't a problem in this case, right? There's no concern about dividing by 0 except with regard to this entire radical. So here we need the radical 9 minus x squared minus y squared minus z squared. That whole thing needs to be strictly greater than 0, right? Not greater than or equal to 0. If it's equal to 0, then we're dividing by 0. So this needs to be strictly greater than 0. Actually, we can leave the radical off. We're just concerned with the expression inside. So that means we would say negative x squared minus y squared minus z squared needs to be greater than negative 9. And then we can reverse the inequality and divide everything by negative 1, right? So x squared plus y squared plus z squared needs to be less than 9, right? So in this case, what is this alluding to? Right? We see that x squared plus y squared equals 9 was alluding to a circle centered at the origin with radius 3. Well, this is alluding to a sphere centered at the origin with radius 3. All right, so this is the sphere centered at 0, 0, 0 with radius 3, right? So this is the same kind of idea. So in this case, the domain of f is going to be the set of triples, x, y, z, that lie inside a sphere of radius 3. Okay, so it's kind of the reverse of the previous example and also like bumped up into the third dimension as well. But that's kind of the idea here, right? So the domain is not, it's never going to be as straightforward here as it is with functions of a single variable. And kind of everything just sort of gets knocked up a notch or two in terms of complexity when you're talking about functions of several variables. Okay, and so again, just an intro. So a lot of the things that the way you already think about domain, it's going to extend here. It's just going to be potentially a little more complex. Now, a lot of the combinations that we're used to with functions of single variables can be extended to functions of several variables. So things like this, if I have f plus or minus g of xy, that's going to be the same thing as f of xy plus or minus g of xy, for example. Okay, you can add functions like this. Multiplication works the same as well. Right, so that's f of xy times g of xy. Right, so kind of similar, well, the same as what we had previously seen. And then, of course, things like this, division works the same as well. Okay, now where we run into a little bit of a wrinkle is when we talk about composition of functions, right? So it's not possible to combine two functions of several variables, but what you can do is you can take a function of several variables and compose it inside of a function of a single variable, right? Now I think if I write it out, it'll be a little clearer. So g composed of h of x comma y, right? This would be, the way you would write this is g of h of x, y. Now here, g is a function of a single variable. Right, and now hopefully that makes sense, right? So if I plug in an x and a y into h, I'm going to get one number out of it, right? So I don't get two numbers to then plug into g, right? When I evaluate h, I get a single number, and that single number can be plugged into g, right? And so composition works like this, where g is a function of a single variable, and h is a function of several variables. right? It doesn't have to be just x and y. It could be x, y, z. It could be, function of 4 variables, whatever. But the function you're going to plug that into has to be a function of a single variable. Okay, now what about the domain in the case of composition? Well, in the case of composition, we would say the domain is going to be the subset of the domain of H such that H of x, y is in the domain of G. So let's write that down. It's hard to just, so the domain here the domain of G composed of H is going to be the subset of H, right? So H is going to have some domain, clearly. It's going to be the subset of H such that, when I plug those x, y's into H, that evaluates to something in the domain of G. Okay, so you need to know what the domain of G is, and then you, for all the values x, y in the domain of H, all of the hxy's that are in the domain of G is now in the domain of the composition. So, I mean, kind of common sensey. It's sort of the same as the other, functions of single variables, right? But, you just need to kind of take into account that the interior function is a function of more than one variable. So that it could be more complex to identify the domain of that function on its own. Okay, but otherwise it works the same way, works similar. Okay, and we'll talk about lots of different functions throughout the rest of the course. But the big ones we should point out here: polynomial functions, right, can be extended into functions of several variables. So functions of the form, functions that can be written as the sum of they can be written as the sum of expressions like, like some constant times x to the m power, y to the n power, where, c is a real number, of course, and then m and n would be in z plus, right? So the positive integers and 0. So, or 0, right? So you want to throw the 0 in there as well, of course. So just the same as the regular description of polynomials, right? With the exponents have to be positive whole numbers or potentially 0, right? And that's all we're saying here. But it works. It's the same definition, right? So things like f of x, y equals 2x squared y to the third power plus 4x y to the fifth minus 6x y, for example, is a polynomial in xy. Okay, so that's an example of just how polynomials are kind of extended into functions of several variables in a really natural kind of way. Okay, and then the other type that we should mention here is the case when you take a ratio of polynomials and you get a rational function. All right, so rational functions also exist as the ratio of two polynomials. Right, so just like with the single functions of a single variable. So things like this. Like something like that, right? So this is a rational function. Right, in xy. And so, yeah, again, just the exact same definition as with functions of single variables, just extended to now allow for multiple independent variables. Okay. All right. So as I said, this was kind of a shorter section, right? But we just want to kind of introduce some of the ideas of functions of several variables because we're going to need it. Because we're going to now begin doing calculus on this type of expression. So functions that have more than one independent variable. That's going to be kind of the focus of really the rest of the course. So we're going to be, how do we take the derivative of this? How do we integrate this? And so this will bring us into the world of partial derivatives, right? Partial derivatives, and into the world of multiple integrals, which will really be kind of the focus of the rest of the course. Partial derivatives and multiple integrals. I mean, and of course other things as well, all these applications, but we'll get into that. So we'll kind of start on the differentiation side by talking about limits and continuity for functions of several variables. Then we'll get into partial derivatives, differentials, and a bunch of differentiation techniques. And then some applications. So we're going to kind of, from this point on, we're going to kind of mirror Calc 1 and then Calc 2, like specifically how to differentiate and what can we do with derivatives, and then how to integrate and what can we do with integrals. Okay, and specifically of functions of several variables. All right, so eager to get into that, and but this will be all we need to cover in the main for functions of several variables, and the rest of it we'll pick up as needed as we kind of venture off into this. So I will leave it there, and we will talk to you all next time. Take care.